Hi, this is Dr. Brian MacDonald, author of Practical Stress Analysis with Finite Elements. Welcome to the next video in our FEA101 series. So this is our 8th video in the series, which is an introduction to FEA for new users. So in the last video we looked at the theoretical overview that we're going to use for all the various elements we're going to look at. And today we're going to start off and look at the first type of element, which is the simplest element, which is a truss element. So truss elements can also be called link or spar elements depending on the FEA software you're using, and they essentially can just extend or compress axially. So that's all they can do. They get longer or shorter along their own axis. They cannot bend and they cannot change cross section. So think of a line that can change its length and orientation in 2D and 3D cases, not in 1D obviously, but cannot bend. Good examples of problems that can be analysed using trusses is things like bridges and roof joints. So here these would be a 2D truss analysis. So as a roof structure. And in 3D we could have things like space frames again. So again, the point being that each of these individual members here or here can get longer or shorter along their axis, but they can't change. So they can't bend. In the case of these 2D ones and 3D ones, they can also change the angle they make with the reference axis. We're going to start off by looking at a one-dimensional truss. So we've already looked at this element in the video on interpolation, and essentially it's a line that can expand or contract in one direction. It has two nodes and a linear interpolation of displacement within that line. So here's our element here. It's got two nodes, I and j. We've set our natural coordinate origin at the center of the element, and we set up a natural coordinate system such that node j has the eta, or natural coordinate of 1, and node I has a natural eta coordinate of -1, and the element has a length L. So we have this mapping function here which allows us to convert between local coordinates and natural coordinates. So x is our local coordinate. So for example, if we had the local coordinate here at node I, the origin of the local coordinate would be there, and so node I would have a local coordinate of 0, and normally node j would have a local coordinate of whatever length the element is, which would be L. Okay, so we can use that local coordinate, we can use the length of the element, or we can convert any point in the element to a relative natural coordinate. So again, we went through this in the video interpolation. So if you're a bit confused by what I'm talking about here, maybe go back and look at the interpolation video. So we then have our shape functions, so SI and SJ. So SI is the shape function associated with node I. So remember, it'll have a value of 1 at its own node, a value of 0 at the other node. And then conversely for node J, it'll have a value of 1 at its own node and a value of 0 at node I. And again, they're very, very similar. They're essentially half 1 minus eta, where eta is the local coordinate, or sorry, the natural coordinate, and SJ is a half 1 plus eta. So by putting in various values of eta, we can calculate the shape functions at those values. So for example, let's say we wanted to calculate the shape functions here at the middle of the element. We would set eta equal to 0, and we would essentially get a half 1 minus eta, which is a half. And we'd also get a half 1 plus eta, which is a half, which makes sense because, as I said, SI goes from 1 at its own node to 0 at the other node, varies linearly, which means it's a half in the middle here, and vice versa with the other element. So with the other shape function. And again, we went through all of this back in the interpolation video. So again, if you're a bit confused, please do go back and have a look at that. So we can then relate displacement of any point in the element to the displacement of the nodes ui and uj. So ui is the displacement of node I, uj is the displacement of node j. We've already said what si and sj are. They're the shape functions. So once we know si and we know sj, and we know the displacement of node I and the displacement of node j, we can find the displacement of any point in the element by setting the eta of that point and using this equation here. Okay, so we can find the displacement of any point once we know the displacement of the nodes and we know the shape functions. Okay, so again, that's for interpolating displacement within the element using the shape functions. So if we then take a look at strain, so we have a value for displacement here. If we take a look at strain, we have strain is equal to, in one dimension, du dx. Okay, we only need to consider displacement in the x direction, which is u, and we're talking about differentials in terms of dx, which is the one direction we're looking at. The problem here now is we want to work out du dx, but we're already working in the natural coordinate system eta. So that means we need to kind of somehow deal with this du dx. So luckily we can use the chain rule. And the chain rule basically says, well, du dx is the same as du d eta times d eta dx, because essentially the etas will cancel and leave us with du dx. And we can work out what du d eta and d eta dx are. So d eta dx comes essentially from differentiating this equation here in terms of x, which will give us 2 over L. So again, 2x over L, differentiate that, gives us 2 over L. And then du d eta we can find from here by differentiating the shape functions si and sj in here. So again, that's what is shown here. I'm saying that, well, at this point here, I've got 2 over L du d eta. And now I can say, well, du d eta is the same as dsi d eta dsj d eta times u. Okay, so I'm taking this here and putting it down here, and just the u is simply a list of numbers, so there's nothing to differentiate in that. S has terms of eta, which means I can differentiate in terms of eta. So u is almost like a constant and comes out of the differentiation. So I'm left here with 2 over L dsi d eta dsj d eta times u. Dsi d eta gives me minus a half. Dsj d eta gives me a half. So I can again multiply that in there, and I end up down here getting, well, strain is equal to 1 over the length of the element minus 1, 1 times u. So minus 1 and 1 is just this one row matrix with 2 elements in it. Okay, and then if I go and compare this to my general form here, I can say, well, I always have strain is equal to this strain displacement matrix B times the nodal displacement vector u. Now I've already got that in the form I want here, so that tells me that this bit here is the strain displacement matrix. So again, there's the strain displacement matrix for this element. It's 1 over L minus 1 and 1. And once I have that strain displacement matrix, then I can get equations for stress. So stress is equal to D times strain, where D is the material property matrix. So in this case, D, because we're only dealing in one dimension, is going to be E. So it's going to be Young's modulus, so we're elastic modulus. So we're assuming that we have a linear elastic material in this case. So obviously, if we weren't doing that, D would be something different. For the moment, we're just going to assume in one dimension we have Hooke's law in one dimension, and D is just the elastic modulus of the material. So we can replace D with E, and we can replace strain with B times U, as we have done back here. So now we have an equation here for strain, which is B times U, and here for stress, which is E times B times U. Okay, so the important thing from this screen then is we've got an expression for stress, we've got an expression for strain, and we've got an expression for displacement. Okay, so we can rewrite displacement in terms of nodal displacements and shape function matrix. We can rewrite strain in terms of a strain displacement matrix and the nodal displacement vector. And we can rewrite stress in terms of E times B times U. So we've got equations for our expressions for all of those. So let's look then at the general form of the total potential energy equation. So this is from the last video. So we talked about the potential energy equation, and we said that essentially that the total potential energy in a static system is given by the strain energy term, which is this bit here, which is a half the integration over the volume stress times strain, and then the work done, the external work. So we have the body forces times the displacements they cause, surface loads times the displacement, and point loads times displacement. Okay, so we need to apply this equation here to our truss element, and as I mentioned on the last slide, we already have expressions for U, strain, and stress. Okay, we can also determine dx from our mapping function. So our mapping function said that the natural coordinate was twice the local coordinate divided by the length of the element minus 1. So we can differentiate that, and we can play around with that equation, and we'll find that dx is equal to L over 2 d eta. We have a one-dimensional element, so these v terms here are either going to become A dx or just dx, where A is the cross-sectional area. So we're going to assume that the cross-section does not change as we go along the length of the element. So we have a constant cross-section. So that will allow us to convert that dv to A times dx. And then in certain cases, we can just have a direct change to dx when we're dealing with stress and strain, because they're not dependent on area. We're just talking about they vary along the length of the element. We can also assume then, as I kind of already said this, that A was constant in the element, but we're also going to assume that the body force and surface load is constant within the element as well. So, putting those four assumptions into our general form of the potential energy equation, we get this here. So now we're saying that for a particular element, it's going to be half the integration in the element of the stress in the element times the strain in the element times dx. So we've gotten rid of that dv, we've converted it to dx. And then in terms of the body force term, we've replaced the dv with a dx. In terms of the surface load, we've replaced that with dx. And this term remains the same because, as I mentioned in the previous video, this is already in a discretized form. It's already applied to points. So remember, effectively what we're doing in a finite element analysis is dividing our problem up into nodes and trying to apply loads and work and apply boundary conditions and work out the displacement of those nodes. So it's a discretized problem. So this part already is discretized because it's a point load applied to a point and talking about the displacement of a point. So we kind of want to get everything else into that kind of form there. Okay, so let's just move on from here then. So just restating what we had there. Now what we're going to do is we can fill in the known values. So remember, we know what stress is, we know what strain is from a couple of slides ago. We also know that little u, which is general displacement or in the element, is the same as a big S times big U, so shape function matrix times nodal displacement vector. So again, U just means displacement within the element in general, whereas large U means the specific displacement of the nodes, which is something we can either measure or we will know. So putting all those in here makes this look a bit more complicated, but it's actually, we'll see in a minute, it's actually a bit simpler to apply. So what we've done is we've replaced strain with B times U. We've replaced stress with E times B times U. We have replaced our body force then in here with the shape function times U for the U bit. Okay, and in here again in the surface load, we've got the shape function times U as well. Okay, and then we have various other terms that come in here. So comparing this to the general form of the minimum potential energy equation then so this is our general form of the potential energy equation here, which basically says by applying this to a specific element, we generally get something of this form here, where we have U times K times U. So if you look up here, we've got U, we've got this bit in the bracket here, times U. So obviously the K is going to be equal to this bit here, which is EAL divided by 2, the integration between minus 1 and 1, B transpose times B d eta. So again, we'll know everything in here. So when we use a particular element, we'll normally apply a material property to it. So we'll know its Young's modulus. We know the cross-section area of the element. We know the length of the element. By using eta, we've set the limits of integration between 1 and minus 1. And we know that B is the strain displacement matrix from previously, which is 1 over L, 1 and minus 1. So we can put all those things in there, and we end up with this here. So once we do this B transpose times B and integrate between 1 and minus 1, we get this matrix here. So the stiffness matrix for a one-dimensional truss is EA over L, 1 minus 1 minus 1 and 1. Okay, similarly for the force terms, then we can say, well, if we have the body force term, it's going to be the area times the length divided by 2 times the body force that's applied to the element, and how it's split out between the nodes is given by this equation here. So if we work all this out, we get a half AL body force per unit volume, 1 and 1. What that means is if a body force is applied to the element, that's how it's split to the two nodes. So remember, in FEA we can only apply a load to nodes, but a lot of the time in the problem we're going to specify that we're applying it to an element. So A, again, is the cross-sectional area of the element, L is the length of the element M, and FMB is the body force per unit volume applied to the element M. Now we're going to look at an example in a minute and we'll make it kind of quick, bit more clear what all of this stuff is. And finally then the surface load, if we need to use that as well, will similarly be split between the two nodes according to this equation here, which again is the surface load times the length of the element divided by 2, and that's applied equally to the two nodes within the element. So we'll see when we look at more advanced elements, we won't always have this 1 and 1 here. You know, we could have a case where we have 1/3 applied here and 2/3 applied down here or something different, okay? But in the case of this element, they're both applied equally. Okay, the load is distributed equally across the two nodes. So as I said, a lot of this stuff is kind of difficult to understand, so the best way I find to understand it is to take a look at a quick example. So we're going to look at a very simple example here. We have a stepped solid shaft. It's got a circular cross section. We're given the diameter of those cross sections there. It supports a load of 100 newtons at its free end at the bottom. It's attached to a rigid surface at its top end, so we're going to assume that it can't move up there. The shaft is made from steel, and we're given the material properties. We're given the elastic modulus of 210 gigapascals, and we're told that the density, rho, is equal to 7,850 kilograms per meter cubed. We're asked to use two linear truss finite elements and determine the stress distribution in the shaft. So what we're going to do is we're going to use two elements. We're going to say, well, that's one truss element, that's another truss element. We're going to assume it's a one-dimensional problem acting vertically, so it's held here as a load down here, so all the loads and reactions are in one direction. So we're going to assume there's no left and right behavior or in and out of the page behavior. So let's take a look at that. Let's build a finite model of that and take a look. We're also asked to consider self-weight due to gravity. So as well as having the 100 newtons acting down here, we also have a body force on both of those elements due to gravity. So here's our finite element model showing here. So we've two linear truss elements. So again, a linear distribution in each element means two nodes in each element, one at each end. The local node numbering is shown on the right. So if I look at the first element here, element number 1, its I is up here and its J is there, so I1 and J1. Whereas the next element down here, its I2, so its I is there and its J is there. So basically this node 2 is the J node for the first element and it's the I node for the second element. So that's what we're trying to say by these numbering on the right here. The global node numbering is on the left, so then we're just, from a global perspective, just going to say, well, we're going to call the nodes 1, 2, and 3. Okay, and the element numbers are out here. So this is element number 1, and this is element number 2. So we can form the element stiffness matrices then. So from our equation earlier for the element stiffness matrix was the K for each element is EA over L, which are the values for the particular element, 1 minus 1 minus 1 and 1. So for element number 1, K1, is going to be the Young's modulus or elastic modulus, which is 210 by 10 to the power 9, 210 gigapascals. The length of the element is 0.1 meters, and we were told that it had a diameter of 0.1 meters, and that's a radius of 0.05. So pi r squared, so pi times 0.05 squared will give us the cross-sectional area of that element. And I have 1 minus 1 minus 1 and 1. And what I've done on the outside here is I've written the global node numbers or global degrees of freedom. So I've got 1, 2 and 1, 2. So element 1 joins nodes 1 and 2. So I've written 1, 2 across here and 1, 2 down here. Similarly then for the other element, so element number 2, same Young's modulus, pi r squared again, but we've got a different r here because that has a thinner cross section than the one on top. Same length, 0.1. Again, 1 minus 1 minus 1 and 1. So the inside of the matrix here is the same because they both have that going on. But on the outside, I'm going to write 2 and 3 and 2 and 3 because element number 2 joins nodes 2 and 3. So 2 and 3 and 2 and 3. So again, I have 1, 2 here and 2 and 3 here. Okay. So what I want to do now is, this is just repeating what I had on the previous page, which is rewritten out here. I want to put the two of these together to give me the global stiffness matrix for the problem. Now, to make this a little bit mathematically easier for myself, I'm just going to notice that, well, if you look at K1, it's actually 4 times K2. So the only difference between this equation and that equation is I've got 0.05 here and I've got 0.025 there. So if you maybe just pause the video and take a quick look at that, you'll see everything else in those equations are exactly the same. So this one is essentially 4 times the size of that one. So what I'm going to do is I'm going to rewrite this equation as being 4 times that one. So I'm going to take this one and put it down here, and instead of having 1 and minus 1, I'm going to have 4 and minus 4, minus 4 and 4. Okay, so I don't have to do this. I could multiply all of that out and populate the matrix in here in both cases and put them together that way, but this just makes it a little bit clearer for this example. So now what I'm going to do is going to take both of those and put them together. So my K1 is now this one with the 4s, and my K2 is the one with the 1s. And outside here is the same from both. So I'm going to take that and that. And now what I'm going to do is I'd start with this matrix empty, and I'd write 1, 2, 3 across the top and 1, 2, 3 down the side. And I go up here and I look in both my elements and I go, I've got a 1, 1 here, which is 4, and I've no 1, 1 there. So I just write my 4 down there. And here I have a 2, 1, so I put a 4 there. I have no 2 1s here. I have a 2, 2 and a 2, 3, but I have no 2 1s. And then if I look at 3, 1, that doesn't exist in either of the elements, so I put a 0 in there. Then I go to the next line, and I go, well, I'm looking for 1, so column 1, row 2. Column 1, row 2 here is a minus 4. Doesn't exist in this element. And here's where it starts to get interesting. Column 2, row 2 is a 4 in this element, but I also have a 1 in this element. So I get a 4 contribution from here and a 1 contribution from here, giving me a 5. So at the point where the elements touch, I have a contribution from both elements. So a 2, 2. And then I keep going, and I look for 3, 2. So it doesn't exist in element number 1, but in element number 2 it's minus 1. So I put in a minus 1 there. I look for column 1, row 3. Doesn't exist in either element. Column 2, row 3 only comes from element number 2, which is minus 1. And column 3, row 3 doesn't exist in element number 1, but it's a 1 from element number 2. So that's what I've done here now, is I've put this matrix and this matrix together to give me the global stiffness matrix here. So notice that that's K1, that's K2, and this is just K, because this is the global stiffness matrix for the problem. So now we need to sort our forces out. We've sorted out our stiffness matrix. So the body force per unit volume in each element is given by rho for the element times g. So it's going to be 7850 times g, which is 77,009 newtons per meter cubed. We can now form the element body force vectors. So from our equation here that we had a couple of slides ago. And in this case, we just fill it in. Okay, so we have, let's say for element number 1, it's going to be the area, which is pi r squared, times the length, which is 0.1. And I've just taken the half out there. Okay, so I have 0.1 divided by 2, so that's the L over 2 there. And then the FMB is the body force per unit volume I've just worked out, which is the 77,000. And that's split equally between the two nodes. So if I work all that out for this element, I get 30 and 30. Similar for the other elements, the only difference again being the different radius in the calculation of the area. And again, in this case, I get 7.6 and 7.6. So now what I want to do is put these together. Again, kind of like I did with the stiffness matrix. Again, I've written 1, 2, 2, 3. So row 1 only has a contribution from element number 1, which is 30. Row 2 has a contribution from element number 1 and 2, so it's going to be 30 plus 7.6, 37.6. Row 3 is only from element number 1, which is 7.6. But if you remember from the problem declaration, I also have an F of 100 newtons, so I add that 100 newtons in there as well. So my body force vector, my force vector has the body force vectors from the two elements plus the 100 newtons that's added directly onto node 3. Okay, and that's what I end up with there. Okay, so we can now begin to assemble the global problem equation. So I've got K times U is equal to F. So there's my K, my stiffness matrix. There's my F that I just worked out in the previous slide. And now I have my U. So I've got U1, U2, and U3. But if I go to the problem again and look at node number 1, that's constrained or held. That can't move. Okay, it's got a grounded constraint on it. So U1, or the deflection of node number 1, is going to be 0. Okay, so the displacement of node number 1 is 0, so I put a 0 in there. And that allows me to solve that problem then. So I can solve it, so I can use Gaussian elimination or something similar to solve that. And in this case, I end up finding that the displacement vector is 1 by 10 to the minus 9, 0, which I knew already. Node 2 has moved 8.8 by 10 to the minus 9 meters, and node 3 has moved 34.9 by 10 to the minus 9 meters. So again, this result makes sense because given the loads that are applied and how it's constrained, I would expect node 3 to move more than node 2, and I would expect them to move not very much given how much the loads that were applied. So only 100 newtons applied to a kind of a fairly significant cylinder of steel. I'm not expecting it to move very much, so 10 to the minus 9 meters sounds about right. So then I can go back and use the strain displacement matrix again, the B matrix, and now I remember before I had strain was equal to B times U, and the B in the case of both the elements is minus 1 and 1 divided by 1 over L, and the length of both of them is 0.1, so I can put those values in. And now what I can do is I can take the displacement vector for node 1, which is basically the top two rows here, and put that in there for U. Okay, so that's the U for this element. And then I can multiply those out, so I get that multiplied by this multiplied by that, which gives me the strain in element number 1 is 8.8 by 10 to the minus 8. So again, remember strain is no units. And then for element number 2, exactly the same thing, but I'm taking the second two rows, the bottom two rows here, so with the 8.8 in there, 34.9 in there, and then I multiply this out and I get 2.61 by 10 to the minus 7. And again, that sounds about right. I'm getting very small strain in element number 1 and a bit more strain in element number 2 because it's deforming more. And then the last thing I can do is, I can put those two results together to give me the strain vector for the problem. So remember, because we have a linear interpolation of displacement within the element, strain is a derivation of displacement, which means that we'll get a constant value of strain in the element. Okay, so if displacement is linear, strain, which is a derivation of that, is going to be constant. So if the displacement was quadratic and we derived that to get strain, we get a linear distribution of strain. But in this case, we're going to have one value of strain in each element. So that's the strain vector for the entire problem. And then what we can do is we can multiply those values by Young's modulus. So remember, stress is equal to, in this case, Young's modulus or elastic modulus times strain. So that's going to give us this value here, which basically says that the stress in the top element is 1.85 by 10 to the power 4 pascals, and the stress in the bottom element is 5.48 by 10 to the power 4 pascals, which again seems reasonable. So if we just summarize that, our maximum displacement is 34.9 by 10 to the minus 9 meters, very small, and our maximum stress is 54,800 pascals, which again is very, very small. So what we're just going to take a quick look at now is we're going to jump over to ANSYS Workbench and show the same problem solved in ANSYS Workbench and just show that we get more or less the exact same answer. Okay, so here I am in ANSYS Workbench, and I've built a geometry which is essentially based on the example we just looked at. We've got two truss elements. One has got a bigger cross-sectional area than the other. I've assigned the materials as per the problem specification we just had there. I've assigned the cross sections as defined in the problem. I've meshed the elements with just one element here and one element there, so exactly everything the same as we had in the problem. In terms of loads, then I have a fixed support here. I've put a force down here of 100 newtons, and I've applied standard earth gravity acting on all elements inside there as well. So if I then go and look at my result from solving that, this is my total deformation. So here's my displacement distribution in my solved finite element model, and I can pull up a probe and just take a look at the specific displacement. So the displacement at node 1 is 0, as I'd expect. The displacement at node 2 is 8.8 by 10 to the minus 9, which is exactly what I had in the last problem. And my displacement at node 3 is 3.4 by 10 to the minus 8, or 34 by 10 to the minus 9, which is exactly as I had just on the slide that I just showed. Again, I can look at stress. The stress again is a little bit more is not as clear here, but again we can take a probe and look at it. So I've got 50,000 down here, and I've got 58,000 there. And again, if you look at the result we got, it was about halfway between those two. And again here I'm getting 22,000 and 14,000, and again the result I would have gotten was about halfway between both of those. So in the previous example, we assumed that there was a linear interpolation of displacement within our one-dimensional truss element. But we also could have assumed a different interpolation. So we could have assumed, for example, a quadratic interpolation of displacement. So let's just look at how that would affect things. So if we have a quadratic interpolation, it means we need 3 nodes. Okay, so we now have a new node, which is node K, which is located at the center of the element. So remember, we previously said we had node I located on the left-hand edge, which had an eta coordinate of -1, and node J on the right-hand edge, which had an eta coordinate of 1. So in the center of the element, we have eta is equal to 0. So again, still element of length L, origin of eta, and the center of the element. This new node is there, and this is called node K. So our transformation then between local coordinates and natural coordinate eta is changed. So previously this was a much simpler equation. Now, because we have that third node and we have a quadratic interpolation, now eta is equal to 2x minus xk all over xj minus xi. So if we want to convert any coordinate x into eta, we use this equation here. Remember, we will know what xi, xj, and xk are. They're the coordinates of the nodes, and x is the location that we want to find out the eta of. So for example, if we had this point here, which was a quarter of the way along the element, we would put its x coordinate in there. We would put the coordinates of the 3 nodes in there, and that would give us our eta coordinate for that x coordinate. So again, as I just explained there, it maps natural coordinates to local coordinates. Our shape functions then are very much changed again. So you might remember previously for the linear truss, where we didn't have the third node, we had simply SI was a half eta minus 1. Now it's a half eta times eta minus 1. Again, so we're getting that eta by eta term, or that eta squared term, which makes a quadratic interpolation. So previously it was a linear interpolation. So again, we have a half eta times eta minus 1, we have a half eta times eta plus 1, and then we have 1 plus eta times 1 minus eta. So again, each of these equations, if you multiply them out, are quadratic equations, because they all have an eta squared term. So they're the shape functions. And again, we can relate displacement in the element in general to the shape functions and the nodal displacement vector. So this is a list of the displacement of each of the nodes. These are the shape functions for each of the nodes. And we can find the displacement at any point within the element once we know the shape functions and once we know the displacement of the nodes. Again, we then try to formulate our finite element analysis. And the first thing we're going to do is look at strain. So in one dimension, strain is du dx. We've already gone over to using eta, so we need to kind of deal with this du dx in terms of eta. So we use the chain rule, and we say that, well, du dx is the same as du d eta times d eta dx, because these two d etas cancel. Du d eta, we can work out from the shape functions. D eta dx is the differential of eta. So again, from the previous slide, we've said eta is this here. So if we differentiate that with respect to x, that is going to give us 2 all over xj minus x. So our strain then is going to be 2 all over xj minus xi du d eta. Remember, xj is the coordinate of node j, xi is the coordinate of node I. And again, we can du d eta, we can expand that out. So remember here, we've just said that u is equal to the shape functions times the displacement of the nodes. The displacement of the nodes here will just be constants. So essentially, if we differentiate the shape functions, we get du d eta. So again, if we do that, we get the differential of si is, in terms of eta, is a minus a half plus eta. Sj is a half plus eta, and sk is minus 2 eta. So now we have our equation in the form E times something u, and normally this is E times bu, and b is the strain displacement equation. So this bit here relates u to strain and vice versa. Okay, so we have our strain displacement matrix worked out. Recall then the from our minimum potential energy equation, the stiffness matrix is going to be given for a one-dimensional truss as EAL over 2, the integration between -1 and 1 of B transpose times B in terms of deta. And now we know what B is, so we can work out this B transpose times B thing. We'll know what the Young's modulus of the material for the truss is. We'll know the cross-sectional area of the truss. We'll know the length of the truss. So we'll know all these constants here. So when we do that integration and multiply these matrices together, we now get the stiffness matrix for our quadratic truss, which is a 3 by 3 stiffness matrix because we have 3 nodes and they have 1 degree of freedom for each node. In other words, one direction they can move in. And so we have I, J, K along the top and I, J, K along the bottom. And we have Young's modulus times Young's modulus times cross-sectional area divided by 3 times the length. And again, we have this 7, 1, minus 8. So previously for the one-dimensional linear truss, we only had 1, minus 1, minus 1, and 1. In this case, because of the B transpose times B, the way these multiply out by each other and the way we have the -1 and 1, we end up with these numbers here. So these numbers are specific to this type of element. Okay, so this is the stiffness matrix for a one-dimensional quadratic truss. So we've worked out our stiffness matrix. We can similarly work out our body force vector. So again, this essentially describes how if a body force is applied to this element, how it's split between the 3 nodes. And what this tells us when we go through all the integration here is we end up with the body force applied to the element multiplied by the area multiplied by the length. And 1/6 of that value is applied to node I, 1/6 is applied to node J, and 2/3 is applied to node K. Okay, so that's how the body force is distributed along the nodes of the element. So remember, a body force is something like gravity, which would act in the entire element, but we can't actually apply a load to an element in finite element analysis. We can only apply it to a node. So this equation describes how that body force is distributed amongst the nodes. Similarly for a surface load, if we have surface load applied to the element, it's distributed in a similar fashion. This time we have the surface load multiplied by the length of the element, and again 1/6 of that applied to I, 1/6 applied to J, and 2/3 applied to K. So now we're going to move on to look at the two-dimensional linear truss. So as its name implies, this element works in 2 dimensions. It's very, very similar to the one-dimensional linear truss that we looked at a few minutes ago. What the kind of applications you'd use this for is things like bridge structures. You can see here it's essentially made out of trusses, roofs, things like a cantilever crane type structure, things like that. So traditionally, bridges and roof structures would be analysed using this 2-dimensional truss. So essentially it's exactly the same as the one-dimensional truss. It's got 2 nodes, I and J, and the truss, all it can do really is get longer or shorter along its length. Okay, so it cannot bend. So basically node I, if this is its starting position here, node I can move up and down and node J can move up and down. And it's in an XY coordinate system. We place it in a Cartesian coordinate system, convenient system for us. And we can realize that the element can be orientated at an angle theta to the global x-axis. Okay, so let's get into how we go about analyzing this. So, first of all, we're going to look at the one-dimensional truss again. And we're going to try and reuse the equations from that to formulate our 2-dimensional truss. So we've already gone through the bother of formulating the one-dimensional truss. Why not reuse that if we can? And so we just use a few little tricks that will allow us to reuse everything that we've already worked out to save us working it all out again. So if we take a look at our one-dimensional truss, so this is the same thing as we had before. Previously I had this orientated horizontally or vertically. Now I'm just going to put it at an angle. And I'm going to say, well, its coordinate system is x dash. So this truss here can only get longer or shorter in the direction of x dash. So let's suppose some load is applied to node J here along, again, parallel to x dash here. And what happens is node I moves from its original position to that position. Node J moves from its original position to that position. So the displacement of node I is ui dash, and the displacement of node J is uj dash. Okay, and the dash, these are exactly the same as what we've just used before. So if I took this figure and just rotated it around so that it was horizontal, it would be the same as the one-dimensional truss that we looked at before. I'm just basically orientating it at this angle. Okay, but it doesn't matter. It lives in its own little universe where all it can see is itself getting longer and shorter along its own length depending on what load is applied to it. So that's all this element understands. So again, it's in its 1D coordinates. Its displacement vector, we now call that u dash, is given by ui dash and uj dash. So ui dash is displacement along the direction of the element. Uj dash is displacement along the direction of the element. So now we're going to say, well, that same element can exist in a 2D space. Okay, so 2D Cartesian coordinate system. So we've got x and y. So x is on the horizontal, increasing towards the right, and y is rotated 90 degrees anti-clockwise from the positive x axis. That's the definition of a Cartesian coordinate system. And if we look at that and we just have our element exactly the same, nothing's changed, but now we're just saying, well, it's orientated at an angle theta to the global x-axis. Okay, so we've just taken that same thing and we just stuck an xy coordinate system there and said, well, it's got an angle theta. Now, if we look at the displacement of node I, ui dash, so it just moves from there to there, that is the same as saying, well, it moves a little bit across in the x direction and a bit in the y direction. So as we all know from vectors and vector analysis, moving from this point to this point, in other words ui dash, is the same as going ui plus vi. Okay, so ui is displacement in the x direction in the 2D coordinate system, and vi is displacement in the y direction in the 2D coordinate system. So we can say that ui dash is equal to ui plus vi. So again, there's no dashes on these ones. The dash is in the direction of the truss or in its own 1D coordinate system. So the one-dimensional displacement ui dash is equal to the two-dimensional displacement ui plus vi. And we can do the same for node j. Again, so node j moves from here to here, which is a displacement of uj dash. And that is exactly the same as going across uj and up vj. Okay, so a certain amount in x and a certain amount in y. So now we can say that in 2D coordinates, the deformation, which is u, which doesn't have a dash, is ui vi and uj vj. Okay, so the big difference here is in one-dimensional coordinates, our displacement vector u dash has two rows because it just has the deflection of node I and the deflection of node j in the coordinate system of the element. Whereas in 2D coordinates, our displacement vector u without a dash has four rows because it has the x and y deflection of node I, and then it has the x and y deflection of node j. Okay, so we've got the same thing, exactly the same problem, but we're looking at it in two different coordinate systems. So again, just to summarize, here's what we had in the last page. So we can use elementary trigonometry and vector algebra to say that, well, ui dash is going to be ui cos theta plus vi sine theta. Okay, again, this is just going back to very simple vector algebra. And similarly, uj dash is equal to uj cos theta plus vj sine theta. So we're relating the deflection in one dimension to the two-dimensional deflections and the angle that the element makes with the positive x-axis. So the above equations, that there can be expressed more conveniently in matrix form. So again, I have my one-dimensional deflection ui dash uj dash here. I have my two-dimensional deflection here, ui vi uj vj. Remember, that's displacement in the x and y of I, displacement in the x and y of j. And then I have cos theta sine theta, cos theta sine theta. So again, if I multiply those out, I will get exactly this set of equations here. So we essentially have one-dimensional deflection here, two-dimensional deflection here, and something relating them. So that something relating them is called the transformation matrix, and we give it the symbol L here. Okay, so we've got u dash there, we've got u here, we have L relating the two of them, and L is cos theta sine theta 0 0 0 0 cos theta sine theta. And we often give these cos and sine thetas a symbol because it occurs so often in mathematics. We call them direction cosines. So L and M are the direction cosines. L is cos theta and M is sine theta. So again, if you've done any study of vector analysis before, you'd have come across these. Okay, so direction cosines are used quite a lot. So again, L just means cos theta, and M is sine theta, and theta is the angle that the element is making with the positive x-axis. Okay, so now we can relate displacement in one dimension to displacement in two dimensions via the transformation matrix L. So let's adapt our earlier one-dimensional linear truss equations so that they work for the two-dimensional truss. So now that we've done this, we can just take all the equations that we worked out before and play around with them a bit, just use this transformation matrix essentially and turn them into two-dimensional equations. So rather than reinventing the wheel, we're reusing them. So if you recall, strain energy in 1D local coordinates was given by this. So we had a half u dash k dash u dash. So previously we'd just call that UKU, but now because we're saying it's the one-dimensional version, we're saying it's the dash. So this is the equation we had for the one-dimensional truss. So putting u dash is equal to L times u, which we just worked out in the previous slide. So wherever we have u dash, we replace that with L times u. So u dash becomes L times u. U dash becomes L times u. And remember, u is just a constant, so we keep the L, k dash, L together. But we know that in 2D global coordinates that strain energy is going to be u times k times u. So if we look at both of those, it's kind of obvious that k is equal to L, k, L. Okay, so the stiffness matrix in two dimensions is the stiffness matrix in one dimension, which is k dash, which is pre and post multiplied by the transformation matrix. Okay, so we have the transform of the transformation matrix there to allow us to multiply it in. So if we take a look at that, so we've just said that the stiffness matrix is going to be L, k dash, L. We already know that L is that, and we already know that k dash is that from our one-dimensional truss. So if we multiply those together, we get this. We say L k dash L. So here we have our EA over L. We put that out there. There's the rest of our k in there. There is L there. And there's L transpose. So transpose, we just replace the rows with the columns. So the first row of L becomes the first column of L transpose. The second row of L becomes the second column of L transpose. And if we go through and multiply all those out, we get this here. So this is our stiffness matrix for a two-dimensional truss, two-dimensional linear truss, and you can see that it's based on the Young's modulus of the material making up the element, the cross-sectional area of the element, the length of the element, and L and M and L squared and M squared. So L is the cos theta, M is sine theta. So we'll know what all of those are because we'll know the angle that the element is orientated towards the positive x-axis. So similarly, we can form the strain displacement matrix in 2D then. So we had the strain, so we're going to say, well, strain is equal to B times U dash. Okay, and we can replace the U dash with L times U. Okay, so that means that we have B, which we had for the one-dimensional truss, multiplied by L times U. So if we multiply this by L, we get 1 over the length of the element, minus L, minus M, L and M. So now we've gotten the two-dimensional version of the strain displacement equation. And element stresses can be obtained in the usual manner then. We just simply multiply that by Young's modulus. So that's all that's happening here. I'm going through the same procedure. I'm just multiplying Young's modulus in there, and I've got this with Young's modulus over it, and I've got this with Young's modulus over it. So that gives us an equation for stress. Or we could just work out strain first and just multiply it by Young's modulus. So let's take a look at an example then applying all of that. So we have two truss elements arranged as per the diagram. So we're going to assume that the left-hand edge, in other words these points here, are held rigidly to prevent movement in any direction. So it could be bolted onto a wall or welded to a big steel structure or something like that. So just basically these points can't move. The pin joint here supports a vertical load of 10,000 newtons acting vertically upwards. We're given the truss cross-sectional area. We're told it's 0.05 meters squared. And we can assume that the trusses are made from steel with a Young's modulus of 210 gigapascals. And then we're asked to find the deflection of the pin joint on the right-hand side and the stress distribution in the truss framework. So let's have a look at our finite element model then. So we've created a finite element model that consists of two elements, element 1 here, element 2 here, node 1, node 2, node 3. So elements and nodes are numbered in an anti-clockwise direction. So again, node 1 is here, node 2 is here, node 3 is there. So again, that's the convention in finite element analysis. It won't make a huge amount of difference if you do it another way, but it just makes things simpler. And again, it is the convention, so it's best to stick that if you can. So let's make a table of known and easily calculated data. So first of all, we're going to know the coordinates of each of the nodes because we're given that in the previous page. So we're going to say, well, node 1 has an x and y coordinate of 0. Node 2 has an x coordinate of 2 and a y coordinate of 1.5. And node 3 has an x coordinate of 0 and a y coordinate of 1.5. We can then work out what element 1 consists of node 1 and node 2. And element 2 consists of node 2 and node 3, and they're the I and j nodes. Okay. The length of the elements we can calculate quite easily using trigonometry. And then we can work out the cos and sine of the angle that the element makes with the positive x-axis. So if you look at element number 1, the cos of the angle that makes, and again that can be worked out from trigonometry, is 0.8. The sine it makes is 0.6. Element number 2, remember it's going this way, okay, so the angle it makes is coming from 0 all the way around, so element 2 is orientated at 180 degrees from the positive x-axis, so it's not 0 degrees. Okay, if it was going in the opposite direction over here, that would be the case. So because of that, L is minus 1 and M is 0, okay, so the cos of 180 is minus 1 and the cos of 0, or sorry, 180 is, sorry, the sine of 180 is 0. Okay, so that's very important. Element number 2, look, node 2 to node 3, that's its I, that's its j, it's going in 180 degrees, not 0 degrees. So now we can use the data in the table to form the element stiffness matrices. So the first element we put in all the data, and remember this is just L squared, and again this is M squared, and so on, and we put in the different values here and we get this. And again we do the same for element number 2. Now what I want to do is I want to make sure that these go into the right place in my global stiffness matrix. So element 1 links nodes 1 and node 2. So we have U1, V1, U2, V2, because we're talking about the U, or the x direction displacement, and the V, which is the y direction displacement. So U1, V1, U2, and V2. So that's element number 1. Element number 2 has U2 and V2, node 2, and U3 and V3 of node 3. So it's very important that I put those labels in on the stiffness matrix because that allows me to put the things into the right place. So then if I go on my next slide, I'm going to try and put these together. So first of all, let's take a look at element number 1. Okay, so if I compare the two elements, first of all, I can see that I've got 210 by 10 to the power 9 times 0.05 divided by 2.5, and here I have the same thing divided by 2. Okay, so what I'm going to do is when I put something from this in here, I'm going to divide it by 2.5. When I put something from this one here, I'm going to divide it by 2. So let's just take an example of the degree of freedom U3, U3. Okay, so if I come over here, U3 and U3, I've got 0.5 because that's 1 divided by 2. Okay, again, if I look at U1, U1 here, it's 0.64. If I divide that by 2.5, I get 0.256. Okay, so essentially what happens is I'm working my way through here. I go U1 and U1, that goes in there. V1 and U1 goes in there. And again, if I start off with an empty matrix here and label it U1, V1, U2, V2, U3, V3, and same down here, and I just look for the elements in here that go in there. And the only time I'm going to have a problem is when I have ones that contribute to both. So if you look at it, for example, U2, U2. So U2, U2 is 0.64 divided by 2.5 from here. And it's also got U2, U2, a 1 from there as well. So here I get this 0.256 plus 0.5. So it's got a contribution from both. I think that is the only one I think that has a contribution from both. V2. So if I look then at V2, U2, it's got 0.48 from here, but V2, U2 here has got a 0. Okay, so it doesn't have the, that's why we don't have the addition. V2, V2 is 0.36 from here, and again V2, V2 has 0 from there. Okay, so the only one that actually has something gone in from both is U2, U2, only because there's zeros in this one here. So again, if you pause the video here maybe and look, make sure you're happy with where each one of these comes from, okay, and just work your way through each element, and you should see quite easily where they come from. Okay, so now I have my global stiffness matrix assembled. And now what I can do is I can assemble my global problems. Remember, my global problem is K times U is equal to F. So in this case, there's my K that I just worked out. Here's my U, which is U1, V1, U2, V2, U3, V3. And my F in this case is going to be the X direction force on node 1, the Y direction force on node 1, X on node 2, Y on node 2, and so on. So for each node, I have a U1 and a V1 and an X force and a Y force. Okay, so now what I'm going to try and do is put in known values. So from my problem, remember node 1 and node 3 were fixed, so that means U1 and V1 is 0, and U3 and V3 are 0. And then the only node that had a load put on it was the vertical 10,000 load that was placed on node 2. So again, these are all 0, and fx2 is 0, but fy2 is 10,000. Okay, so that was the only load that's put on there, so I've got zeros everywhere else. So now I can solve this problem because I have a lot of zeros in here. So if I look at the next slide, so here's what I just had at the bottom of the last slide. Now what I want to do is identify lines that basically say, well, something multiplied by 0 is 0. Well, that's trivial, I know that. So I can get rid of those lines, and if I get rid of that line, I need to get rid of that column as well. So here you can see if I'm getting rid of row 1, I need to get rid of column 1 as well. Okay, and again, row 2, I need to get rid of that because I've got 0 is equal to 0. Row 5 and row 6, and I get rid of column 5 and column 6. And that leaves me with these 4 in the middle, and those 2 and those 2. Okay, so I'm left with this here. So obviously that's a much easier problem to solve than having to solve this big problem here. So now I can solve that. I can multiply it out, or I can solve it using Gaussian elimination, whatever I want. Solving that tells me, well, node 2 is going to move 0.2539 by 10 to the minus 5 meters and in the horizontal direction, and it's going to move 1 by 10 to the minus 5 in the vertical direction. So that means that the global nodal displacement vector is this here. So again, node 1, x and y, no movement. Node 2, minus 0.2539 by 10 to the minus 5 in the x direction, 1 by 10 to the minus 5 meters in the y direction. Node 3 doesn't move. So the strain in the element can now be evaluated. And again, we just use the equations we previously worked out. Now, because we have the global nodal displacement vector, we can work this out. So for element number 1, it's the first 4 lines because it's node 1 and node 2. So we put those first 4 lines in here. We multiply it by our strain displacement matrix. And again, remember that's made up of L and M, and that's just the length of the element. And that gives us the strain in element number 1 is 1.5873 by 10 to the minus 6. Same thing for element number 2. And again, remember element number 2 is nodes 2 and 3. So that's the bottom 4 rows of this. And in this case, the strain is 1.2698 by 10 to the minus 6. We can put both of those together to give us the strain vector for the entire problem. So we've got 2 elements, so we're going to have 2 strains. And then we can calculate the element stresses by basically multiplying those strains by the Young's modulus, which in this case is 210 by 10 to the power of 9. And we get the stress in both elements. And something different we haven't looked at towards now, or up until now, is getting the reaction forces. Okay, so sometimes we may want to know the reaction forces as the support. So let's consider the global reaction equation. So here we have R is equal to K times U minus F. And if we expand out that equation, we can say, well, R is going to be the reaction force of node 1 in the x direction, the reaction force of node 1 in y, of node 2 in x and y, and of node 3 in x and y. K, we already know what that is. We worked that out. U, we'll know what that is. Okay, we already know that because it's the displacement of node 2 and 3. We just worked that out as well. And also we know what the force vector is as well. So again, we can work on that. So this equation only needs to be evaluated at the fixed degrees of freedom. In other words, where U is equal to 0 and F is equal to 0. In other words, lines 1, 2, 5, and 6. So lines 3 and 4 of the above equation do not need to be considered, so we can take out 3 and 4. And when we go and do that, if we find out that we get the reaction force of minus 13,000 in the x direction at node 1, plus 13,000 in the x direction at node 3, and minus 10,000 in the y direction at node 1. So then if we consider balancing up everything in our system here, we've got a minus 13,000 and a plus 13,000, so they balance each other out. We've got a minus 10,000 reaction force and a plus 10,000 force, so again that's balanced in the y and in the x direction. Okay, so the next thing we're going to do is jump over to ANSYS Workbench and take a look at this same example as it's done in ANSYS Workbench. Okay, so I've recreated the problem in ANSYS Workbench. It's exactly the same dimensions, same material properties. I essentially have 3 nodes here, and I've got the trusses joining those 3 points. In terms of meshing, I've made sure that I've just got one truss element. So each line is divided into one truss element. So it's exactly the same as the problem that we just went through mathematically. I've applied a force on this node here of 10,000 newtons, and I've got 2 fixed supports here and here. So there's my 2 fixed supports shown with the purple tags, and there is my vertical force shown in the red arrow there. So then when I went and solved that, I can look at the directional deformation. Okay, so this is here it's exaggerated the deformation, so I can just go up here and just put it down to the normal deformation. So again, I'm getting a deformation of minus 2.486 in the x direction. So when we solved that, we got minus 2.539. So again, it's reasonably similar. Okay. And then in the y direction, I'm getting a max deformation of almost 1 e to the minus 5. I'm getting 9.77 e to the minus 6. So again, very similar. Then if I look at stress, you might recall that the stresses that we just worked out were 0.33 megapascals and 0.266 megapascals. So again, we got 3.26 rather than 3.3, and we've got 2.61 rather than 2.66. So it's very close. And then the last thing we'll just look at is our force reactions. So here, my force reaction here in for this one here, I'm getting a 13,000. So again, in our example, we got 13,333. So I have 13,009, which is close enough. And then my other reaction was I'm getting 9,800. And in the numerical example we just did there, we had 10,000. So again, all quite close. Okay, so the last thing we're going to look at in this video is the 3-dimensional linear truss. So essentially this is the same thing. It's a truss element with 2 nodes I and j, but now we can move in 3D space. So it's got x, y, and z movement allowed. So previously we had ui dash was basically a function of the x and y components of displacement. Now ui dash is going to be related to the x, y, and z components of displacement. So if you like, node I here not just moves on the page, but can move in and out of the page as well. Why we would need to use this kind of element? Things like space frames, like this is a very good example. Also, any kind of crane type structures, box crane type structures, bicycle frames. So there's another example on my channel here using a bicycle frame, and I think I might actually use beam elements for that, but you could also use these 3D truss elements as well, or things like these small support structures or things like that. So anything that's in 3D space and is made out of trusses, essentially space frames. So again, we're going to reuse that same theory again and more or less do exactly the same thing as we did with the 2-dimensional truss. So in our 1-dimensional coordinate, we have this. We have u dash is equal to ui dash, uj dash. In other words, all along the length of the truss. And in 3-dimensional coordinates, we're going to say, well, the deflection of the element is going to be the deflection of node I in the x, y, and z directions, and the node j in the x, y, and z directions. And we're going to try and relate this to this, And we're going to do exactly the same thing as we had before, and we're going to use a transformation matrix. So we can relate 1D and 3D coordinates via a transformation matrix. So u dash is equal to L times u. In this case, the transformation matrix, because it's 3D, has 6 columns and it has 2 rows. Okay, so we've got 2 nodes, so we've got 2 rows, and we've got 6 columns because we have a u, v, and a w for each of the 2 nodes. So L, m, and n are the direction cosines of the local x-axis with respect to the global x, y, z axis. So if we have this in x, y, and z, then if this is u going here, then the angle theta that it makes with the x-axis, cos theta, is going to be L. The angle that it makes with the y-axis, again, that cos of that angle is going to be m. And then the angle it makes with the z-axis, the cos of that angle, is going to be n. Okay, so as before then, k is going to be equal to the transformation matrix times the matrix in 1D, so that's just our 2 by 2 matrix, times the transformation matrix again, and we multiply this out, we get this here, we get a 6 by 6 matrix. So it's 6 by 6 because we've got 2 nodes with 3 degrees of freedom, or 3 possible ways of moving at each node. So 2 by 3 is 6, so 6 by 6. And again, this is just a combination of the different direction cosines L, m, and n. The strain then can be calculated from this here, again using the same procedure as we used with the 2D, and the stresses can be evaluated from this here. So there isn't really a great jump in going from 2D to 3D if you understand the 2D, the concept of expanding the one-dimensional coordinate system to the two-dimensional coordinate system. Essentially, you're just doing the same thing here with the three-dimensional version, only you're just adding in another dimension. So again, exactly the same procedure is followed, and you end up with a set of useful equations that have effectively been derived from the one-dimensional equations. Okay, so that's it in terms of trusses. So let's just have a review of what we went through in this video. So first of all, we introduced the one-dimensional linear truss finite element, and we formulated an FEA using that element. We then carried out the same finite element analysis using ANSYS workbench, and we compared the results. We then introduced the 1D quadratic finite element and demonstrated how using a quadratic interpolation changes the finite element formulation. We then looked at the 2D linear truss finite element and showed how we can adapt the previously developed one-dimensional equations using a transformation matrix to formulate an FEA using this element. And again, we went and did that in workbench and compared the results. And then finally, we introduced the three-dimensional linear truss element, and again showed how we just used that transformation matrix to adapt the one-dimensional truss equations for use there as well. Okay, so that concludes this video. So this is the first element we looked at in detail in the FEA101 series, truss elements. So as always, what I'm doing here is effectively summarizing what's in the book. So if you are interested in finding out more information, or you want to do more thorough study, please do go and buy a copy of the book. And I will see you in the next video.